Welcome back, everyone. We are now moving on to 16.4, free energy. In this section, we are going to define Gibbs free energy and describe its relation to spontaneity, calculate free energy change for a process using free energies of formation for its reactants and products, calculate free energy change for a process using enthalpies of formation and the entropies for its reactants and products, explain how temperature affects the spontaneity of some processes, and relate standard free energy changes to equilibrium constants. I know it sounds like a lot, but don't worry, it's not. So, the second law of thermodynamics we looked at for predicting spontaneity, but we really don't make measurements on the surroundings that are around our system. We usually focus on our system, which limits this use of the second law of thermo. So it's convenient to have some type of thermodynamic function that focuses on just the system but can still predict spontaneity. So just to refresh your memories, the second law of thermodynamics told us that the change in entropy of the universe is equal to the change in entropy of systems plus the change of the surroundings, and it's greater than zero. And when you have a delta S greater than zero, overall you are increasing delta S of the universe, making a spontaneous process. So what we use to focus on the system is Gibbs free energy, delta G. Or you might just say this simply, this is the change in free energy. And this is what we use to predict the spontaneity by focusing only on the system. And this is a state function. So again, it doesn't matter how we get there. The Gibbs free energy, that whatever it is what it is. For my chemistry majors, when you go on to university and you take physical chemistry, this chapter on thermodynamics that we're going over will be a huge part in physical chemistry, and you will be using multivariable calculus to do it. It's actually really, really interesting and pretty cool stuff. I know, I'm a nerd. So delta G is equal to the change in enthalpy minus your temperature times the change in entropy of a system. So the sign of delta G tells us if we're going to have a spontaneous process or not. When it is less than zero, then we have a spontaneous reaction in the forward direction. If it's greater than zero, it is non-spontaneous in the forward direction. And if it's zero, we are at equilibrium. So spontaneous reactions that means they have a negative delta G generally have a delta H less than zero. They are exothermic reactions. And then when you have that negative change in enthalpy, you have this contributing to have a negative delta G. You also tend to have a delta S greater than zero, so you have a positive change in entropy, so that way this negative T delta S stays negative. If you have a negative delta S, then that turns that term into a positive. So having a positive change in entropy will contribute to a negative delta G, which makes sense, right? Positive change in entropy means more chaos, more disarray, which means it's going to be more spontaneous. So you can still have a spontaneous reaction when you have a positive delta H or when you have a negative delta H, depending on how big the other term is, but not both. So if you have both a positive delta H and a negative delta S, you are not going to have a spontaneous reaction because your delta G is going to come out positive no matter what. There is also a temperature dependence, so that temperature really plays a big part in determining the spontaneity of a reaction. So let's go ahead and do this little chart together, looking at the different signs for delta H and delta S, and see how they would come out. So if we have a negative delta H, that means we have a negative and then minus for this minus T delta S, and if delta S is positive, that means we're subtracting a positive, giving us a negative minus positive. That means we get overall a negative sign for delta G, and this is spontaneous. Let's say we have a positive delta H now. and we have a negative delta S. That means we have a negative, so we have positive minus a negative. And when you have minus negative, that makes that positive. So that gives us an overall positive sign. So this is not spontaneous. Now let's say we have a negative delta H and a negative delta S. So then this would be minus a negative. So that gives us a positive. And so it can either give us a negative or a positive depending on how big delta H is and how big the temperature is. So if it's spontaneous, maybe. It's going to depend. So let's say we want to find the temperature at which spontaneity changes from spontaneous to non-spontaneous, or the opposite, non-spontaneous to spontaneous. We need to find the temperature where delta G equals 0. Because at that temperature, so delta G equals 0, that gives us 0 equals delta H minus TdS, so then it also turns into delta H equals T times delta S, and like we see there, T equals delta H divided by delta S. So this is the temperature where we are at equilibrium, delta G equals 0. So at equilibrium, delta H, the temperature of the system in Kelvin, is equal to delta H over delta S. And then that also gives you that threshold. When your temperature goes higher or lower than that temperature is going to change the spontaneity of the reaction. All right, so although the change in Gibbs free energy, it's valid under all conditions. A lot of times we tend to use it at standard conditions. And when you do this, you can use your appendix in your book to get some standard values. So at standard conditions, these are assuming 1 mole, 298 Kelvin, and 1 bar for pressure, I believe. You don't need to remember what the standard conditions are. Just know that you have standard conditions, and so the delta G equation it becomes delta G standard equals delta H naught, or delta H standard minus T delta S standard. So it doesn't really change anything, it just adds that little circle sign. But make sure that you pay attention in your calculations to joules versus kilojoules, because you tend to need joules in the calculations, but a lot of times it's given to you in kilojoules. So that is very important that you pay attention to that. So let's go ahead and look at an example. We're told to use the standard enthalpy and entropy data from Appendix G to calculate the standard free energy change for the vaporization of water at room temperature. And we want to know what this computed value for delta G standard says about the spontaneity of this process. So we're talking about vaporizing water at room temperature, meaning we are going from liquid water to gaseous water. And we know that delta G naught is equal to delta H naught minus T delta S naught. So if you go to Appendix G, what you'll find is it'll give you a bunch of standard values. And so for liquid water, the change in enthalpy of formation is at standard is negative 286.83, and this is kilojoules per mole. So kilojoules, keep that in the back of your head, and then the enthalpy we're given, and this enthalpy, or entropy, sorry, not enthalpy, entropy is in joules per Kelvin per mole. So this one is joules. So notice we have some unit issues here. But for liquid water, its standard entropy is 70. And then for gaseous water, the enthalpy change is negative 241.82 kilojoules per mole, and the entropy standard is 188.8 joules per Kelvin per mole. So very important to notice that there are some unit issues here. So let's go ahead and first calculate delta H naught. And then so here we're saying that's going to be equal to delta H naught of formation. And so that is going to be the delta H formation for our products. Sorry, it's a change in it. So of the gaseous water minus delta H naught formation of liquid water. Okay, products minus reactants. So then that gives us negative 241.82 kilojoules per mole minus negative 286.83 kilojoules per mole. So this gives us 45.01 kilojoules per mole, actually just kilojoules. I'm going to go ahead and rewrite these a little bit. So this is 1 mole times that minus that times 1 mole. So using our stoichiometry just to kind of get rid of the per mole part. So that way we can have the correct unit. So this gives us now 45.01 kilojoules. And we can calculate our change in entropy. So we have 1 mole from our balanced reaction times our product entropy, which our products are the gas, since that's what we're ending with. So we have 188.8. And these are units of joules per Kelvin per mole, or joules per mole Kelvin, minus 1 mole again, times our reactant, 70.0 joules per mole Kelvin. See, moles, 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 moles. And so then this comes out to be 118.8 joules per Kelvin. Okay, and then we know delta G equals delta H minus T delta S. So notice that when we calculated delta H, we got just kilojoules, which we can go ahead and just rewrite this as 45.01 times 10 to the third joules. Or actually, now we'll change the other one to kilojoules. It doesn't really matter. Okay, sorry. So back to entropy. So we have joules per Kelvin, and now we want to go ahead and change this to T delta S. So that means we need to take our entropy, multiply it times our temperature. So which we were told was not 298 Kelvin times 118.8 joules per Kelvin. So those cancel out to give us that term. And then we'll also go ahead and do 1 kilojoule per 1,000 joules. So we have 298 times 118.8 divided by 1,000. And that is 35.4 kilojoules. So now we have kilojoules and kilojoules. So delta G naught is going to equal delta H, which is 45.01, minus T delta S, 35.4. And so this gives us 9.6 kilojoules. So this is a positive delta G. This is greater than 0, so this is non-spontaneous. So remember, for spontaneity, for delta G, has to be less than 0. It has to be a negative. So since delta G here is greater than 0, this is a non-spontaneous process at this temperature. But remember, temperature plays a role. All right, so again, just to kind of confirm the information I was saying with standard, we also do have a standard free energy of formation, which is the same type of thing as delta G, not just this as a standard free energy. And this is the energy change for the formation of 1 mole of a substance from its elements in their standard state at 1 bar and 25 degrees Celsius. And this is pretty much exactly like Hess's law from chapter 5. So for example, you can if you can look up your little mini reactions and it gives you a delta G of formation. And that's also a way you can tell if those reactions are spontaneous in their direction or not. We can also use these delta G formation values to calculate delta G standard. So let's say we have this generic reaction, some Ma plus Nb going to Xc plus Yd. So your delta G standard is going to be your products minus reactants, and so you have your coefficient times the delta G formation for each product minus that for each of your reactants. So it's the sum of the products minus the sum of the reactants. I mean, almost exactly like Hess's law way back in chapter 5. All right, so this equation only works for calculating delta G standard of a reaction at the temperature for which the delta G standard of formation values are tabulated, which is at 298 Kelvin. Okay, so if your numbers, if you're looking at a system that is not at 298, this does not work. Now, the delta G standard formation of any element in its most stable form at standard condition is defined as 0. It's defined as equilibrium. So let's look at an example using standard free energies of formation to calculate delta G standard. So we're going to look at the decomposition of the yellow compound mercury 2 oxide. And it is decomposing to liquid mercury and then 12 oxygens. So we want to find the standard free energy change at room temperature. Delta G standard, I don't know why it popped up twice. And we want to use A, the standard free energies of formation, and B, the standard enthalpies of formation and standard entropies. And we want to see if these results tell us if it's spontaneous or non-spontaneous under standard conditions. So we need to go to the appendix to get some values, and we need to look them up for mercury 2 oxide, liquid mercury, and oxygen gas. So we need to look up delta G standard formation, delta H standard formation, and entropy standard. So delta G is given in kilojoules per mole. Enthalpy is given kilojoules per mole. And entropy is given in joules per Kelvin times mole per mole. All right, so negative 58.43, negative 90.46, and 71.13, 0, 0, 75.9, 0, 0, 205.2. All right, so part A, we're just using those, the Gibbs free energy formation, and this is equal to the sum of the products minus the sum of the reactants. And we can't forget the coefficients. So from our products are liquid mercury and gaseous oxygen. And so we have 1 mole of liquid what the heck did my pen just do? That's weird. Okay, 1 mole of liquid mercury times its standard, which is 0, plus 12 moles of oxygen times 0 also, minus our products, or I'm sorry, our reactants, and we have 1 mole of the mercury 2 oxide, and its delta GF is negative 58.43. So this is a super hard calculation, guys. 0 minus negative 58.43, and we get positive 58.43. 0.3 kilojoules. If you didn't do the multiply times the moles, it would use a kilojoules per mole, but I went ahead and multiplied times the mole. But notice we have 58.43. This is greater than 0, so we're getting non-spontaneous here. And let's go ahead and do this for B using standard enthalpies of formation and standard entropies. So let's start with our delta H standard term. So we have products minus reactants. So that tells us for our products we have 1 mole of mercury times its delta HF, which is 0, plus 12 moles. I think the battery in my pen must be dying or something because it's being really funky. 12 moles of the oxygen times its delta HF, which is 0. Oh, I'm sorry, that's supposed to be 12. That's supposed to be 1/2. That is 1/2 oxygen. I'm sitting there going, this doesn't seem right with its balancing. Okay, that makes a lot more sense, doesn't it? 1/2. I love when copy paste does things like that to me. Okay. And then that is minus our reactants, which is the HGO. And we have 1 mole of that times its delta HF, which is negative 90.46. So then this gets us positive 90.46 kilojoules. And then our delta S term, same thing, products minus reactants, just different numbers. So products, we have 1 mole of mercury times its delta S, which is 75.9 joules per Kelvin per mole, plus oxygen, 1/2, half a mole of oxygen, times its entropy, which is 205.2 joules per Kelvin per mole, minus our reactant, which we have 1 mole of HGO times its entropy, 71.13 joules per Kelvin per mole. All right. And so then this calculates out to be 107.4 joules per mole, or sorry, joules per Kelvin. And now we're going to go ahead and multiply this times our temperature. Since this is standard temperature, room temperature, which is 298.15 Kelvin. So then T delta S, we'll just go put T delta S over here, is equal to 107.4 times 298.15 times 1 kilojoule per 1,000 joules divided by 1,000. So this is 32.02 kilojoules. So then this gives us delta G naught 32.02. It's now a negative because it's negative T delta S, and plus 90.46. So we get 58.45 4 kilojoules, which is pretty much the exact same answer that we got before. This is greater than 0, it's non-spontaneous. And I'm going to change this to negative T delta S, so that way I can just kind of do it like that. So both ways of doing this got us the same answer. But remember, if we were given this information at any temperature that was not 298, using method A would not work. All right, so far we've been talking about free energy change, delta G, and we're doing this with the standard free energy change. So we're at 1 bar pressure, partial pressure, 1 molar concentration. So we do actually have an equation to calculate delta G under non-standard conditions. And this is it right here. So delta G is equal to delta G standard plus RT ln Q. Remember that one from last chapter? It's back. Our reaction quotient, good old R universal gas constant, and our temperature T. So far we've also talked about delta G standard has to be negative for a reaction to be spontaneous. We actually do have another measure of reaction spontaneity using equilibrium constant K. So to be spontaneous, K has to be greater than 1. Okay, and remember K depends on your concentrations of products divided by reactants, assuming they're either gases or solutions. And this also makes sense because when we talked about what the different numbers for K, when it's greater than 1, the reaction product is favored, which means the reaction is going to go in the forward direction. So if we are at equilibrium, remember delta G equals 0, and Q is equal to K at equilibrium. So if we take the starting equation and we plug delta G in for 0 and K in for Q at equilibrium, then that goes away and we end up with delta G standard is equal to negative RT ln Q, or times the natural log of K. Sorry, not Q, K. So we're talking equilibrium constants. Kind of cool, right? I guess. And this holds true for all of our equilibrium constants that we have talked about in this course. Kc, Kp, Ka, Kb, Kw, Ksp, Kf, Kd. So many Ks. And so now we can use standard free energy change of a reaction for the extent of a reaction. It's pretty cool. So this really starting to tie in everything we've been talking about so far this semester. And just like enthalpy, free energy changes for reactions are additives as long as your third reaction, your overall reaction, is equal to the sum of your first 2 reactions. So then delta G3 equals delta G1 plus delta G2. And then keep in mind, if you reverse a reaction, the sign on delta G is reversed. And if the reaction is multiplied by some n, then so is delta G. Just like enthalpy. So highly recommend, if you're going, what are you talking about? Go review chapter 5. Your book also gives you this nice little summary of scenarios for enthalpy and entropy changes, what can happen. So this would be a nice thing for you to have, like when you're taking an exam or doing homework, to just have to reference it. And then these are some plots showing free energy versus reaction process for different systems that have standard free changes either being they're either negative, positive, or 0. And then showing non-equilibrium systems will proceed spontaneously in whatever direction is necessary to minimize free energy and establish equilibrium. So it's something, when you're bored, you can look at these graphs, but it's just to give you some examples. This next thing is showing plots showing the variation in delta G with temperature for the 4 possible combinations of the positive and negative signs for delta H and delta S. So we kind of went over earlier, but just kind of relating everything, bringing it all together. So another nice thing to have on hand. So we're going to go ahead and finish this chapter with a few examples. And by a few, I think I mean 1, 2, 3, 4, 5 examples. As I know that's what you guys just love. So, is a reaction coupling the decomposition of zinc sulfide to the formation of hydrogen sulfide expected to be spontaneous under standard conditions? So this example is using coupled reactions. So kind of bringing in a bit of what we did in chapter 15. So we first need to go ahead and use Appendix G for these reactions. So the first reaction we have is the zinc sulfide decomposing. So ZnS, it's decomposing, meaning it's forming zinc solid and solid sulfur. And delta G standard, we're going to call this delta G1, is equal to 201.3 kilojoules. And then now we're forming H2S as our coupled reaction. So the sulfur from the first reaction is reacting with hydrogen gas to form hydrogen sulfide gas. And this is delta G standard 2. And from the appendix we get negative 33.4 kilojoules. So our coupled reaction, our overall reaction, in other words, we're just going to add everything up. We see the sulfur is our intermediate and it cancels out on both sides. And this simplifies down, if you will, to zinc sulfide solid plus hydrogen gas react to form solid zinc and hydrogen sulfide gas. A good old single displacement reaction. And so remember then the delta G's also add. So delta G3 or delta G total, whatever you want to call it, is these guys added up, and that is 167.9 kilojoules. So this is greater than 0, let's say positive delta G, so this is non-spontaneous. So the next example reaction, we are trying to predict the temperature dependence on spontaneity. So we're told the incomplete combustion of carbon is described by this equation, and we want to know how the spontaneity of this process depends on temperature. So this is combustion. Combustion processes are exothermic. So we know, since it's exothermic, delta H is less than 0 because we're releasing heat. And this is also going to lead to an increase in entropy because we are increasing the amount of gaseous species. So we have 1 mole of a gas on the reactant side, and then we're getting 2 moles of gas from the products. So then we know then that delta S is going to be greater than 0. So because of that, this reaction is spontaneous at all temperatures because we've got that delta H less than 0, delta S greater than 0. That's going to combine to give us, no matter what, a positive words delta G less than 0 at all temperatures. Kind of cool, huh? All right, next example. As defined in the chapter on liquids and solids, the boiling point of a liquid is the temperature at which its liquid and gaseous phases are in equilibrium. That is when vaporization and condensation occur at equal rates. Use the information in Appendix G to estimate the boiling point of water. So this is kind of a cool question because you know what the answer should be, but we want to use this data to see what we could predict it. And so the nice thing about a question like this, for instance, maybe something something like this could come up on an exam, is you have a way to check your answer. Because if you get, let's say you get an answer that's like 542.8 degrees Celsius, that is in no way close to the boiling point of water. So you know something probably went wrong. Okay, so the phase change that we're looking at is going from H2O liquid to H2O gas. And then we're looking at an equilibrium process here because vaporization and condensation occur at equal rates, equilibrium. So boom, that tells us that delta G is equal to 0. So then from our equation, then that tells us that 0 is equal to delta H standard minus T delta S standard. So now we have, that delta H is equal to T delta S, and our temperature at equilibrium is equal to delta H divided by delta S. So now we need to go ahead and use our Appendix G thermodata to get delta H and delta S. So then delta H is going to equal 1 mole of our product, since it's just a 1 for its stoichiometry, and the enthalpy for gaseous water here is negative 241.82 kilojoules per mole. Minus our products, which is our reactants, 1 mole, times the enthalpy of liquid water, which is negative 286.83 kilojoules per mole. And so then this gives us, see, my pen's being really funky. So this gives us 44.01 kilojoules for delta H. And then delta S, we have 1 mole times enthalpy for gaseous water from our products is equal to 188.8 joules per Kelvin per mole, minus reactants, 1 mole times 70.0 joules per Kelvin per mole. Boom, boom. Oh, and we're going to go ahead, I'll come back to it. Okay. So then this comes out to be 118.8 joules per Kelvin. And I'm going to go ahead and rewrite the delta H term as 44.01 times 10 to the third joules, because we actually we need to get our energy units to cancel out. It doesn't matter which one, if we want to use joules or kilojoules, because they're going to cancel out anyway. But yeah. Okay, so now our temperature is equal to delta H, which is 44.01 times 10 to the third joules, divided by delta S, 118.8 joules over Kelvin. So now you can see where our units come into play. 1 over K brings that Kelvin back up to the top. And this gives us 370.5 Kelvin. And then if we go ahead and subtract 273.15 from that to give us degrees Celsius, we get 97.3 degrees Celsius. So that's pretty close to 100 degrees Celsius, right? This is reasonable agreement, only a couple degrees difference. And then also keep in mind that the enthalpy and entropy changes that we used here were from standard data, which is at 298 Kelvin. If we were to have enthalpy and entropy change data that were closer to the actual boiling point of water, so if they were at 373, we'd probably be even closer in our numbers. All right, so let's look at another example, calculating delta G under non-standard conditions. We want to know the free energy change for the process shown here with these specified conditions. And my subscripts didn't work as well as they're supposed to, but that's okay. I'm just going to go ahead and, gotta love copy paste from the internet. All right, so we're given the reaction, we're given a temperature, we're given partial pressures, and we're given a delta G. So recall that delta G under non-standard conditions is equal to delta G standard plus RT times the natural log of Q. And so we can go ahead and look up delta G standard for this reaction. And the back of the book and the appendix tells us that delta G standard is equal to 33.0 kilojoules per mole. And we can go ahead and just rewrite this times 10 to the third joules per mole plus R, which is our good old friend 8.314 joules per mole Kelvin, times temperature. We're told 25 degrees Celsius, which we need to add 273 to give 298 Kelvin. So 298 K for T. Boom, boom. Times the natural log of Q. And so then this is going to be our equilibrium. So we have partial pressure of H2 cubed. So that's 0.250 cubed times our other product, which is nitrogen, partial pressure of nitrogen to the first power, 0.870, divided by our partial pressure of our reactant, which is ammonia squared, and we're told is 12.9 squared. So once you punch all this into your calculator, simplify it down, you're going to get 9,680 joules per mole. And this is a positive value of delta G, it's greater than 0, so this is non-spontaneous at these conditions. Your book is really obsessed with non-spontaneous conditions, apparently. All right. Example 16.13, this is the last example and the last thing I have for chapter 16. We're given the standard free energies of formation of silver plus, Cl minus, and silver chloride are that stuff. Respectively, calculate the solubility product, KSP, for AgCl. Okay, so first things first, let's write our reversible reaction. AgCl is in equilibrium with Ag plus aqueous plus Cl minus aqueous. And we know also from this KSP, solubility product depends on the concentration of silver times the silver ion times the concentration of the chloride ion. So let's go ahead and first write our equation for delta G under these conditions. So since we're given standard free energies, this tells us we don't have to use like the our other equations. We can go ahead and use delta G standard, and we can calculate this doing products minus reactants. So from our product side, we have silver, we have 1 mole of silver times its delta G formation. Since we're doing standard stuff, it's okay to use these values. And it has a delta G formation of 77.1 kilojoules per mole. Plus our other product, we have 1 mole of chloride times its standard delta G is, where am I? Oh, there it is. Negative 131.2 kilojoules per mole. And we're subtracting our reactant, all one of them, which we have 1 mole of AgCl times its delta G, which is negative 109.8 kilojoules per mole. So this delta G comes out to be 55.7 kilojoules. Okay. So also recall that at equilibrium, we had that delta G standard is equal to negative RT times the natural log of K at equilibrium, which is what we're talking about here. And so then if we want to solve for K, we know that we can go ahead and say the natural log of K is equal to delta G naught. Put the negative sign here, divided by RT. So then solving for K, we need to take the E and put it to the negative delta G standard over RT, and that is equal to K. So now we also have another equation at our disposal for doing some problems. So now K is equal to negative delta G, which is this negative 55.7, and we're going to rewrite this times 10 to the third joules. Oh, apparently I didn't really need to use this. Okay, doesn't matter. Okay. And then this is going to be divided by R, 8.314 joules per mole Kelvin, times our temperatures to 98.15 Kelvin. I'm just going to rewrite this. This is e to this whole power, or you can put exp and then all that. It doesn't really matter. And also, technically we can say this is joules per mole, even though we added that in our calculation. We didn't actually need to, but it doesn't matter. So then this gives us K is equal to 1.74 times 10 to the negative 10th power. And then if you were to look in Appendix 3 for this K value, you would get, oh, this is KSP, sorry. You would get a pretty reasonable agreement. So Appendix J has some K constants. So that does it for Chapter 6. This is a fairly short chapter, but you get lots of time to stew on it, which is very beneficial for you guys. All right, I hope you guys are doing well. As usual, if you have any questions, please let me know. Hopefully this is more of a fun chapter for you and things are starting to come together more. All right, stay safe and know that I'm very proud of you guys. See you soon.